Hi, Jörg. Can you hear me okay?
Yeah, I can hear you. I just saw your message. So
Perfect, perfect. No, I just wanted to say thank you for taking the time. I really appreciate it. And I guess I should give you a quick intro so that the folks who have joined us uh, have an opportunity to meet the person who they're going to be speaking with today. So for everybody, thank you again for joining us. And just a quick word: the official talks for the formal sessions, not the workshops, but the formal conference sessions, will take place tomorrow. So check on your email for the hopin.to email for that. So yeah, Jörg is actually based in San Francisco, if I'm not mistaken. Jörg, is that correct?
I'm split between Berlin and San Francisco, and right now I'm stuck actually in Berlin. But yeah.
Oh, very good. So it's actually afternoon there. Uh, Good to know. And he's the head of machine learning for ArangoDB. Previously, he had worked on machine learning pipelines in healthcare and finance with distributed systems and at Mesosphere. And I'm just actually cut off here. Sorry, 1 second. Having and in memory databases. Sorry about that. Just going to minimize the screen. So Jörg received his PhD for research around distributed databases. Very cool. And data analytics. He's a frequent speaker at meetups, international conferences, and lecture halls. And we're very grateful for him to take the time to contribute back to the community here and spend time with this workshop. So with that being said, Jörg, I will put myself on mute. I'm assuming that folks know that they could ask questions. I'll leave it up to you if you want to answer the questions during the event or at the end. And if you have any questions during the end of the event, feel free to go and take your time to answer those as you have time permitting. The other thing I was going to mention is I know that we've increased the time for this a little bit. So if those who can't make the full event, feel free. I think we're going to take a break in the middle, if I'm not mistaken. So as your calendar permits. So with that being said, I will pass it over to Jörg, and I hope you enjoy.
Thanks so much for the introduction, and also thank you so much for organizing this really cool event. So I've been really looking forward to this. And what I like about it is the general tendency of basically how can we get machine learning into production. Having worked with many large and medium-sized enterprises in the past trying to leverage machine learning, I actually felt this was kind of the biggest challenge overall. A lot of them were building data science teams, hiring data scientists, building like this one cool project, but then in the end actually getting value out of it and leveraging that was one of the biggest challenges. So this is also why I'm kind of like grateful for this talk, because we'll focus a bit about, like, as you can already see here, on everything which is around the core machine learning part. Most important thing, despite that on the slide, is actually the link down here, because that's the link to the slides. And you will see, and also if you have to drop off early, the slides, it actually includes much more than we possibly can cover in this workshop. So it was originally designed to be like a 1.5 day workshop where we also went a bit more into detail. But I left a lot of slides hidden in here, and there's a lot of extra material. So if you want to deep dive into some of those topics, I would just recommend, keep the slide deck. Also feel free to share. It's open source. It's also an open source slide deck. So most important part right now would be to copy this link here. I can also just additionally paste that actually in the chat for most people. And with that, we can then also get started. If you have any questions, feel free to raise them at any time. Oh, it's already here. Thank you so much for copying that over here. Saves me some time. And then we can actually get started. So kind of the agenda, as said, it's based around a lot of the things you can do in machine learning if you need to build like an operational data pipeline. So I often got asked, like, how do those different technologies like MLflow, TFX, Airflow, Jupyter, how does it all fit together into a picture? And even more importantly, where should I start with that? So if I only have like a certain budget within my company, what is kind of like the most valuable thing to start? And I kind of try to use that as kind of like the driving agenda to get like from easy stuff to more complex stuff here as kind of a curriculum. If you have any particular questions and you would like to dive into a certain topic, please write it in the chat so we can focus on that. And as I said, there are probably more slides anyhow than we can cover. But in the end, it's kind of the goal, and at the end is that you have an understanding what does it take to build like a full-fledged data science platform, from like the ingest of data and streaming, versioning of data sets, over to model serving, monitoring of features, a feature catalog, the orchestration of that entire platform, sharing of notebooks and sharing of existing code with model libraries, and then also a little bit into resource and service management, but I don't think we'll have too much time to dive into that. Yeah, and as mentioned, like the challenge is actually like how much time can we spend on this? But yeah, this is why we simply have more slides than we can possibly cover. So you can either suggest what you want to dive into, what you want to focus on, or you can also read up on other topics in more detail, just using the slide deck. So yeah, as asked in the beginning, it would be really helpful to understand who you are, what's your background, and what's your expectation. So what do you want to get out of this workshop? And maybe you can just write that in the chat so we can try to focus the workshop on your particular expectations. While you write that, let me briefly switch over, even though I had that great introduction from Dave already. So I'm the head of engineering and machine learning at ArangoDB. So that's a multi-model database, also open source database. And prior to that, I always have been switching back and forth between databases and large scale infrastructure, in particular machine learning infrastructure. So I first got my PhD in distributed database systems, but also focusing a lot on like data analytics. So you obviously come in touch with machine learning as well. Then back at Mesosphere, building up large-scale infrastructure also for machine learning, for example, for Uber, Apple, Airbnb. So basically kind of the resource layer you see down there. Then switching over to Suki AI, building machine learning pipelines for healthcare. And then now switching over to ArangoDB, where I can actually combine both those passions of databases and large-scale infrastructure and machine learning, which is actually pretty cool and a pretty nice combination. Just to kind of cover the marketing part and why do we actually care from a ArangoDB side about something like machine learning. So ArangoDB, it's an open source native multi-model database. So if you imagine like a graph database like Neo4j and a document database like Mongo and maybe Elastic, they had a kit together, that would kind of be ArangoDB, because we can handle all those different models inside one database engine, and it kind of avoids having to build another layer on top. It's distributed, which also poses up challenges if you want to deploy that on large-scale infrastructure, but it's also super useful if you're actually diving into graph-based machine learning. We have AQL, a SQL-like query language, and also ACID transactions. And there was a really interesting article, I think it was early this year, March sometime, mostly driven by Microsoft. So cloudy with a high chance of database systems, 10-year prediction for enterprise-grade machine learning. And that article, the link is also down here, kind of covered this convergence of databases and enterprise-grade machine learning. Because if we want to deploy machine learning in large-scale production scenarios, we actually have to re-implement a lot of the stuff we already have in databases, like data provenance, data audit logs, permissions, where we can make sure only certain people get access to certain data sets. And we actually have to track all of that. So this is, in my opinion, a pretty cool intersection of those two worlds, which we can combine. And this is what we also see a lot from a ArangoDB side, on customer sides, people who use this native multi-model database to implement their machine learning infrastructure. I actually also gave another workshop that was at ODSC earlier this year about graph-powered machine learning. A link is down here. So again, similar, it's a slide deck with a lot of links to do Jupyter notebooks. So if you want to learn a bit more about graph-powered machine learning, feel free to just copy that link and try out those examples. But this is basically why we on ArangoDB side are so interested in machine learning, and also in particular about machine learning infrastructure. Okay, kind of starting with that first block, and as mentioned, feel free to ask questions at any time. Also here, there was like this one notion about experiences. Feel free to ask about how stuff works out in production use cases. I'm happy to talk about trade-offs, for example, between the different solutions, stuff we tried out, stuff I would do differently now. So at any point, just feel free to put that up in the chat here. So why machine learning is taking off right now, or why is it such a hype topic? And in the end, why does it turn kind of those data scientists into superheroes? We can do a lot of stuff we just weren't able to do before. So for example, drug-based discovery. Also, if we're looking at the COVID stuff, this is happening here a lot. I debug, it's kind of like a composing framework, and I found it even really hard to distinguish whether that song was composed by a deep neural network or whether it was composed by Bach himself. And so I was hoping for one more slide there, but yeah. In the end, this is actually because we have a lot more compute resources available. We have a large number of new research results, but most importantly, we simply have large enough data sets available. Dave, is it okay if I mute you? Someone is unmuted and I hear a lot of background noise. So thanks.
I think I should be muted. Let's see if I could just ask everybody else to mute.
It's okay. It just sounded a bit rough in the background. So yeah, what is the challenge? If we have this cool new world, we have large data centers, large data sets, cool new algorithms, it's kind of the expectation. So for this data scientist being the superhero, what we kind of expect them to be doing is they get like a data set, they write a really cool model, we train that model, it has really cool outcomes, we run that model, and then we can actually put them on the next problem. And this is what I still see happening with a lot of companies who focus on hiring a data science team and then expecting to get a really fixed and fast output from them. Unfortunately, what's kind of the reality, and I assume most of you have actually seen that image by now, it's from a paper by Google talking about the hidden debt in their machine learning systems. So basically, where do they spend resources for machine learning? And we see only the small black box in the middle. This is the actual machine learning code, whereas everything around is kind of the serving infrastructure, data collection, data verification. So basically, most of the time they spend on machine learning is spent outside or pretty far away from machine learning code. And this is also what I've seen is that this gets severely underrated as an investment. But in the end, just keep in mind, this is what's actually getting the business value out of machine learning. It's not necessarily the model itself. It actually happens here if you serve it and you actually get some output from it. But to do that right, you actually need the entire infrastructure around that. So if you kind of look at it from kind of the other side, there's those two main phases. First of all, there's the experimental phase, and then there's the production phase. And each of them, they are not static. They're pretty dynamic, and it should be a constant iteration. So experimental phase, and this is where still kind of like people or data scientists are kind of starting with. It's we identify a problem, we choose some data, we build our machine learning and code our model, and then we experiment a bit, we tune the hyperparameters, then probably start over because we have identified, hey, we actually need more data or we need to change our features here. Once we actually came up with a certain model, we need to move that into a production environment. And I've actually seen companies where those two phases, they are pretty distinct. So there is this team of data scientists who kind of do that initial model finding. And then there's another team and they will actually recode the machine learning algorithms, potentially in another language, in another framework for the production environment. And in that production environment, it's in general more about how do I build like a stable data pipeline. So if we look back at like data analytics, often this is actually pretty similar. So we have a data transformation where we clean up data, where we normalize data, then where we generate features. From those features, we can then train our models. And then we have like a model library from where we can actually serve those models for either online or batch predictions. Again, important there is actually to monitor the model performance to actually figure out, oh, now it has changed between the initial data characteristics have changed. I have a different data distribution than in my initial data set I used to train the model. So I actually should adapt that model as well. All right. So in the end, what I kind of would pitch or the general idea is that similar as in software engineering, where we came up with really cool principles like continuous integration, testing, and we actually have our own courses at colleges or universities about software engineering. We actually need to establish similar principles for data science. And this is where we are early on, but we as a community, if we kind of work together and establish them together, this is actually saving each individual entity a lot of work, whereas formerly only companies like Apple, Google, Uber, they could actually spend the resources and large teams to kind of figure out those best practices. And I think this is, if we work together as a community, share those experiences, share those best practices, this is going to be super helpful. And this is why I'm a kind of a strong believer in those open source principles. So this is also something what, for example, Google and other companies are realizing, that the value in that entire machine learning ecosystem is not so much in the code, but it's actually in the data combined with code. So even if I publish something like TensorFlow, it's a lot of value and a lot of engineering hours went into that. But overall, the main value I get out of machine learning models, it's just if I have a model together with the data to actually train it. And other people actually have similar opinions. So for example, Ian Goodfellow, that similar to software development, we need a sort of best practices also for machine learning. So other people who drive a lot of development in that field of machine learning have similar opinions about data science principles. So if we kind of want to map that out, the first question we should always ask ourselves is, do we actually need machine learning, or can we use machine learning? So similar to those companies throwing a lot of data scientists at a certain problem, I feel that sometimes machine learning is kind of overhyped right now. And we just try to solve a lot of problems with, for example, deep neural networks, which A, we don't really need machine learning for, and B, we could probably also use like a more simple like regression model and get even better results. So kind of before starting anything in machine learning, we should actually ask ourselves, do we actually need that? And is it applicable? What kind of data sets do we have? What is the quality? And also what is the quantity? What is kind of the serving environment? So do I need a model which is going to run in a car? Do I have a model which is running in a large distributed Google data center where I can leverage TPUs or something else? What kind of model architecture do I need to use? Can I actually leverage a pre-trained model so I don't have to develop and train a model from scratch? What is the amount of training resources I can throw on that? And what is also kind of the model freshness? So how often do I need to retrain that model? Is it just like a one-time model which is going to stay stable over time? Or do I kind of need to update that over and over again? And I feel those are kind of important questions I should ask before actually starting a particular problem. Machine learning overall, and there are a number of other really good courses for that. So I just feel that right now we are focusing on like this unsupervised models where we follow this hype of deep neural networks, but there's actually a lot of other things in that space which can be useful. And not everything has to be solved by deep neural networks. And one course I would really recommend if you're new to machine learning and you kind of want to get an overview of the entire field is fast.ai or deeplearning.ai. They have really good overview courses for free for most of the stuff. But as deep learning and deep neural networks, they have this new hype. Let's briefly stick there and kind of see where is that coming from or what is the promise. So in traditional machine learning, I typically have a data scientist doing some feature extraction. So we get an input like a dog picture, we extract some features, and then we can use something like an SVM or something for classification, and we get like our output dog or not dog. Deep learning kind of promises to incorporate that feature extraction part into code simply by throwing in a lot more data. So we just give it like a lot of pictures which are labeled dog or not dog, and then the feature extraction can actually be done by the model, simply kind of replace the human by data. This works in some cases, but it's kind of, I would say it's just a promise. And the more we invest into feature extraction, data cleaning, and data preparation, the more value we'll get actually in the end out of this model. So kind of the insights or ideas of that, of a deep neural network is kind of like it's structured into different layers. The first layers can identify very simple distinctions, for example, like lines, or basically switching between different from like dark to very light regions of a picture. Then the second layer is accumulating and assembling those first features into more complex things like a nose or eye. And then the final layer can decide whether it's a dog or not. So the overall process, and that's still true for any kind of machine learning model, is first we have the training step. This typically happens in like large data centers, and it takes hours, days, weeks. We get a lot of input data. We train our model, in this case, a deep neural network, and then the output is kind of a trained model. The second part, and again, this is where you actually get value out of it, is the inference part or the serving part, where we leverage that trained model. We give it one input, for example, like a picture we want to classify. and then that pre-trained model can classify that. In general, this is, again, this training, especially this training part, because this is a resource intensive part, is a very iterative process. We're not just going to train a single model, we will train a lot of models over time with different hyperparameters, or also update them if we get more training data over time, or for example, if something changes. So for example, if, imagine you're trying with like different cleaned up data sets or different camera models. It might be that because the camera model you took those pictures with is changing, that you might want to retrain your model because of different lightning parameters and so on. So in the end, like this trained model ends up being an entire model library. So the second challenge is kind of the personas. We already talked about that superhero in the middle who can develop all those cool models. But in a real enterprise scenario, this is way too much for him to deal with. This entire picture we saw earlier was like a serving environment. We have a large distributed training cluster. So he actually needs kind of like a few sidekicks. And kind of this most common sidekick we're seeing up becoming more and more popular is the so-called like data ops or ML engineer. And those people, they kind of combine two skills. Whereas a data scientist, most of the ones I know, they have a very strong mathematical background. They really understand those models really deep. The data ops engineer is kind of the DevOps version for data science. And so they usually combine two key skills. So first of all, they understand data science, they understand what it means to build a model, but they also understand distributed systems engineering. So they understand how to set up a cluster, they understand how to monitor a large distributed cluster, and those are the people who will actually get your production value out of your machine learning models. So the kind of typical division, and this again is pretty similar to that division we saw earlier between the experimental and prod, is that the data scientist, they take care of the data, they take care of the cleaning and preparing the data sets. They will develop a model, for example, using a Jupyter notebook or Python environment. Then they will export that model. And then the data ops, they're actually responsible for having set up an infrastructure for training that model that can either be using like an old style. So the first machine learning systems we built, we actually used Jenkins for that. Nowadays, I would probably refer to Airflow for manage the entire pipeline, but we'll get to that later during this workshop, where again, we train it on the full data set, we do model testing, model optimizations, then we store that model plus the associated metadata, and then we serve that model and expose it to actually real life customer requests. And yeah, as mentioned, this process can actually be pretty disjoint. So in finance, I've seen such kind of pipelines or built such kind of pipelines where actually the data science parts, they don't even get access to the real data set. So they get like a scaled down anonymized version of the credit card data set, and that they can use to explore and build their models. But once they hand it over to the automated pipeline, that pipeline actually has access to the real life data set and can train it on the full data amount, non-anonymized possible. And then the data scientists, they basically just get feedback, hey, your model performed in this or this way, and this can help them to actually reiterate on their model. But given data privacy concerns, so this is probably most relevant in healthcare or finance, but also with GDPR or now CCPA, this is also becoming probably more relevant for all of us building machine learning models. Okay, so this is typically this distinction where data scientists, they're really focused on data, doing science with data, building the core model, and then the data ops is responsible for retraining, training it at scale, and then also serving it later on. This is bringing us to TensorFlow and Jupyter. So TensorFlow, probably most of you, I assume they know it. I would say it's a software library for machine intelligence. It easily lets you code models. It doesn't even have to be Python nowadays. And then that gets executed into or transformed into code, which can be executed in GPUs, CPUs, TPUs. There are a large number of frameworks out there. So for example, PyTorch is one of my favorite frameworks besides TensorFlow, but also like Spark, they also have a distributed machine learning library. And there are a large number of other like MXNet, different machine learning frameworks you can use. In many companies I've worked with, actually different teams get to pick different tools. And whereas other companies actually just decide to standardize on one framework. I can see both pros and cons for both approaches. So if we briefly switch back to this image. So if the kind of like model export ends up being in a format which is ignorant of the framework it was trained in. So basically, if I package that in a Docker container or something, then for the data ops or the real-life serving platform, it doesn't really matter what framework is being used. And actually, different frameworks might be most suitable for different models. But overall, using different machine learning frameworks up here for the data scientist, especially here, still makes it more complicated to manage a diverse platform. But overall, it can also be just a personal preference that different teams actually have better experience or more experience with different tools. So it might actually be worth investigating what is the overhead of building this process across different machine learning frameworks. All right, I think that's okay. The next kind of challenge is what kind of IDE, so what do data scientists use to kind of code their things and especially exchange their code. So I still see a number of people using, for example, RStudio, but more and more people are using Swift or especially Python for coding their machine learning models. And I think Python has that advantage that it's really easy to read. So I would always kind of focus on readability more than writability. And the normal constraints of Python, like scalability, don't matter that much, because in the end, it's not the Python code getting executed, but it's basically, it's just kind of like a front end to generate the programs in the background, which is then going to run on the GPU, TPU, or CPU. And so there, kind of as IDE and exchange format, Jupyter has become really, really popular. Because it gives an easy to use IDE. So we can just code in our web browser. And we also have something which is easily exchangeable within a company. There are multiple ways of actually sharing notebooks or making them run. So for example, in this workshop, we're going to use Google Colab to run our notebooks. In the end, you can just put them on GitHub and then provide a link here, which we'll see. And then that environment is spinning up a Docker container and makes them runnable. There's also Binder, which given that we're talking about open source here, probably is the open source alternative we should highlight. And so Binder or MindBinder, binder.org, it actually lets you set up a similar experience internally in your network. So you can turn any internal Git repo actually into like an interactive notebook. And then what you can share with a colleague in the end is just a link to that Binder notebook hosted on GitHub, and we go or in any Git store. It doesn't have to be GitHub, but we're going to see that throughout this workshop. There's also something called a TensorFlow Hub. Let me actually briefly switch back to one of the early slides here. So TensorFlow Hub actually allows you to share full-fledged models. So if I even already have trained a model, I can basically upload it there. And from there, people don't have to train it from scratch. So I feel this is one of the most important parts, is actually how do we share that work being done. And you will see that a large part of this workshop, so basically kind of like those 3 boxes here we'll touch up on, are all about how can I share work between different people. All right, where were we here? So we kind of have this first left. So for people who never run any machine learning framework, so if you come from like a more DevOps perspective, maybe this is something you can actually try out. I will just use it now to show you that kind of like infrastructure, because we're also going to use that throughout this workshop. So here, Colab, what it does, we simply give it like our GitHub. So this is actually hosted on GitHub. We can even look at the source on GitHub. Here we go. And it's a really easy format. We have those different cells. And typically, as you develop that from within the notebook, you don't even have to worry about the cells itself. And the nice thing is, which makes it also for like a perfect exchange format, it combines documentation together with code. So I can simply go in here and then run different code pieces. And now here we see we are connected. So we are connected to a runtime, which right now is hosted on Google infrastructure. And now I can basically run that Python code. I can also, for example, just do print hello world. And we see there's actually Python code being executed. There are different kernels behind those notebooks. So there's also like R integration. There's Julia integration. So we have it here. Even like C++ or other languages being out there, which make it also suitable for different languages. So in the end, in my opinion, a really good way of just sharing work is to actually use Git for versioning, because then I also have a version history and I can go back and using those notebooks, I also have something very simple to share. Of course, this might not be what we actually want to train our models with, but a lot of people actually came up with infrastructure for making that run. And I was hoping I didn't, yeah, it's down here. Yeah, it's gonna come up. For basically kind of extracting the code from our notebooks into like runnable code. So if you're working a lot with notebooks, what I would recommend is, for example, NBDime and NBDiff, because they really allow you for easy merging and diffing of Jupyter notebooks. I briefly showed you kind of the structure of the different cells behind, so this is really hard to kind of compare. But in the end, if I use those tools, they give me a really easy way to kind of like this Git workflow of actually comparing and then also doing code reviews on Jupyter notebooks. And the yeah, I will. There's currently a question about enterprise environments with a lot of restrictions. Maybe you can just tell a little bit about those restrictions, but yes, I will come to that in just 1 second. So the other thing which I find super helpful, again, also in especially in enterprise environments, this has been developed by Netflix, and it's called Papermill. And so this is a tool for parameterizing and executing Jupyter notebooks. So for example, I can parameterize it to run in an data scientist environment where I have access to different systems. But then once I hand it over, it actually runs in the production environment. It will run there with different parameters. And this also basically just allows me to get like an executable version of different notebooks. So if you work in a production enterprise environment, this is going to make it a whole lot easier to kind of differentiate between those different environments. So the typical thing I've seen in restricted environments is that I have this exploratory environment, let's call it this way, where I have access to data sets, where I can actually play data sets. And then there's a very restrictive production environment where I have to deal with data anonymity, where I have to basically also track any data access. And so we've used Papermill in the past to actually make that much easier, and then also kind of make it executable, which is also a pretty powerful feature of Papermill and together with notebooks. I hope that answered your question. Otherwise, feel free to just follow up. Okay. So the question was just clarified. So that in their case, VPC controls on cloud environments, as well as blockages to external websites, such as GitHub or Google Storage. So all of this, let me switch back a few slides. You can just run in your own infrastructure. So for example, here in my binder, it works with your, you will have like a versioning infrastructure in your system. So here you can basically just get the code, you can deploy your own instance, and then it's basically can run against your own Git store. So this can all run within your network. You don't even have to expose any of that. Similar with Papermill and other tools, they don't need internet access. Actually, most of these systems I built on top of them, they were actually in sealed off environments because of the data privacy requirements. So you don't need access to any Google APIs to make that run. I simply choose Google Colab to run this because I didn't want to set up a large-scale infrastructure. And Google Colab is actually pretty generous in donating resources. So for example, here, if we look at our runtime sessions, we can even pick like TPUs and GPUs if we have time later to actually see the difference in runtime. And this is a bit harder with Binder to set up ourselves. Colab is free. Colab, you can kind of pay, and then they have, the pro version where you get preferred access to TPUs and GPUs. But overall it's free, and this is also why I'm using it for this workshop. Any other questions? Otherwise, just write in the channel. So I think the second biggest confusion I've seen in data science project is data quality. So most people, when they start out, and similar here, like I linked this TensorFlow quick start for beginners. And if you start out with that, you're like, whoa, this is super easy. I can just really just focus on the machine learning code. But in production scenarios, this is typically not the case. So typically 70 to 60 to 80% of the time of a data scientist is probably spent on like preparing the data sets, shifting through the data sets. So for example, involving data cleaning, missing or incorrect labels, how do I deal with them? How do I mark what's actually missing or what's wrong? Getting everything in the same format. So for example, here having this workshop across people in US and people in Europe, just having different metric systems. I mean, we have seen space missions fail because of that. But overall, this is also really important to get everything in the same format. Often we even try to get everything in like a similar distribution if that helps us. So if we're training different models, it's often useful to get things on like a certain range of values and also certain distribution if possible, simply because that's going to make models comparable, and also usually it gives us better models. One important thing to keep in mind, because I also have seen people fail there. Let's just say a big automotive company, what they did, they actually invested a lot of time. So they had a running pipeline, and then they had their data scientist building new procedures for data cleaning and data preparation. So they spent a lot of time. They actually trained their models, and they were super happy because the results looked great. Then they took those new models and they actually put them into the serving environment, and they behaved just miserably. What went wrong here? So actually this data preparation part, this is actually also happening here on the serving side. So we also have to do the same steps, the same transformations as it's called, for example, in TensorFlow, on the training data as we need to do on the real life data later getting in for serving. So this is something you should keep in mind. If you're doing some transformations here to your data, they also need to be done here because your models have been trained with a changed data set. So we have a tutorial for that, but I would actually suggest I leave that in here. We can briefly open it and briefly have a look at it. I feel it's a pretty useful one to run through if you have never done so. Where do we have that? Load CSV data. So again, we just click on like run in Colab, and then we can just execute all of this. And yeah, just using that link, you will see that it's free. Downloading the data sets. But what I find useful of it, and that's why I'm just gonna scroll down there. That looks good. I would recommend to actually run that on yourself, by yourself. But kind of what I like about this notebook, that it basically captures the typical steps in data pre-processing you're doing. It's going through the data, like here, for example, numeric features, collecting them, normalizing data. So I felt this was something very useful, combining the different steps of pre-processing data. And then here in the end, we actually training our model, and then we just do some predictions here. So for kind of those steps, if you have never built a production framework, so if you've done kind of the basic tutorials, I would actually recommend to go through here because it captures a lot of the steps you actually need to do to prepare your data sets. I hope this is okay. I would skip over and not do every of the tutorials simply because lack of time. But I would recommend, because it gives to do that later, because it really gives you a good impression of what actually happens in the real world if you haven't done so. The second tutorial, which I find very useful, and this gets us into TensorFlow Extended. So TensorFlow Extended is kind of the ecosystem around TensorFlow. And this already uses the transform components here. So let me see whether I find it on the fly. So the idea is to basically create those pre-processed functions. And those pre-processed functions I can then later on also apply to the serving infrastructure. So here, if you apply the warning, do not change. So you need to plan accordingly. But the idea is to basically create a reproducible piece of code, which is changing your data set or preparing your data set to be consumed by the different models. So this is also something I would recommend to run. Of course, it really gives us, again, the overview. And here, in contrast to the prior thing, it also gives us the kind of best practice tools, at least if you're in the TensorFlow ecosystem. So this TFX, we'll have some slides on later as well. But as mentioned, this is kind of this ecosystem all around TensorFlow, which helps you to build those full-fledged pipelines. Any questions to that? Or also feel free to speak up if we should take like a short break and you actually want to run through those tutorials. Otherwise, I would propose we simply go on with the workshop. We'll take, I would suppose like after the second model, the second part, we'll take like a short break where people then can actually run through those tutorials, and I'm happy to answer questions while you run them. Okay? All right. So let's dive into the first pipeline. So this is exactly where we're going to cover TFX and other pipelines. And so the different pipelines we'll look at is, for example, Kubeflow, which is kind of the TensorFlow on Kubernetes, TFX, TensorFlow Extended, and then there's also the open source platform, or parts of that platform are open source, by Uber called Michelangelo. We'll in particular look at different open source technologies, Kubeflow, TensorFlow serving, TFX, which is a collection of multiple tools. And then we'll also look at different labs, in particular TFX and TensorFlow serving. So again, this is about like, hey, if we just did our first, we trained our first TensorFlow models, so the first tutorial, now we want to kind of get real. And the biggest challenge when people try to get real, I've seen is in model serving. There are actually a number of companies out there who just focus on model serving. So there's, Pipeline AI, for example, from San Francisco. I think they're shutting down a bit, so I haven't seen them that active anymore. And for example, from UK, there's Selden AI. And those companies, they mostly focus on model serving. And I would say this actually has a good reason, because first, it's a hard problem. Secondly, this is actually in the end where you get the value out of your different machine learning models. So it's a very important part. So to kind of get into that, the different challenges, let's look at TensorFlow serving. So TensorFlow serving is the component in the TensorFlow universe which helps us to serve models. We can already see this kind of looks complex because, I mean, in the end, it should be pretty simple. I have a model, I say, expose that model to some live traffic. to queries and then return a result. Cannot be that hard, correct? In the end, it gets more complicated simply because we are not dealing with a single model, but because we actually have a large number of different models out there in the wild, which we want to serve. So if we look at the, sorry, there's just a question. Could you please also advise if we need to serve other model types? Yeah, I'll touch upon that, like XGBoost or IBM. You can, in theory, also cover other model types with TensorFlow serving. So let's have a short look here. And latest, if we later on touch up on MLflow, we'll dive more deeply into different model types. So, but I feel this is actually a useful, despite complex chart, for if we want to understand the different challenges we face when serving different models. So in the end, we get here client request. That's like a servable handle. We don't have to care too much about that. I think this is like an implementation detail. But then in the end, there's kind of the manager of different versions. And this then actually has to pick, I have those 3 different models, which might be different versions of a model. And now I have to pick which one I want to kind of expose that, route this to. So this is kind of this one part. And so what we can actually plug in here in TensorFlow serving is a version policy, which helps us to pick the version we actually would want to expose a certain request to. So we can also have like a filter and say like, hey, in this case, we should pick this one, or we should pick the other one. Where this also comes in handy is, for example, if you have different models which actually have different complexity. So just imagine you're running like a big e-commerce thing, and you want to make recommendations, and those recommendations, that might be a super complex model which actually takes like a second to make a prediction. So you only want to run that in kind of like hours where you have enough CPU, TPU, GPU resources available. But at other times where you actually have less infrastructure available, you want to switch to that other model, which might not be as accurate, but uses much less resources. So I actually have seen that those version policies basically being implemented on the available resources on the infrastructure. So if there are a lot of free resources, we can also spend more for making predictions. But if there is really little available and we currently have a lot of contention, we want to pick kind of like the cheap version being out there. The second challenge, and this is kind of like more here on the right side of the picture, is how do we want to update the different, if a new model comes in. So TensorFlow serving, it's the easiest way to run it is basically from a Docker container, and we can look at into the lab in just 1 second. And it basically can listen to different sources. So that can be a file system. This could even be like a Kafka stream, for example, which we also implemented in the past. And that's the source of different models coming in. And when a new model here comes in, so we just store a new model on the file system, it's being picked up, it's being loaded. And this is also a custom logic you can actually plug in, how to turn that into a TensorFlow servable. And so this is, for example, also one part where you can wrap it if you have other models being available. So many other models can actually be wrapped as a TensorFlow servable. And for example, like PyTorch, I think by now is kind of stable, being served also via TensorFlow serving here. And then this is being loaded in here. As mentioned, this is kind of the the different challenges we have in here, and I was kind of debating which picture to show first. The kind of implementation where most people start out with, which, for example, is just a simple Flask app. So you just have like a Flask wrapper for the API around a container, and then you expose that to the client. That's kind of the most simple version to get a model out there. But I decided to actually focus on the different challenges of you will end up with, because this is in the end where it really gets interesting, and this is also where in the end, in production cases, you will end up with different challenges. So so there's a question with the version policy. We're also thinking about versioning the model and using different versions of that model. Yes, exactly. This is can also be used for that. And to just go into a bit more detail on that, let me switch to the next slide. I think that we can explain it with like from a different view. So, and similar architecture, and this is still a bit hard to be implemented in TensorFlow serving. Of course, this is kind of like a one-to-one correspondence, but a similar architecture I've built and seen is the so-called rendezvous architecture. It was back when Mapper was a thing that they kind of popularized that. And this actually means that I can use different models at the same time. And for different models at the same time, I might have different use cases for doing so. So the first big challenge is that we want to deploy new models with zero downtime. So we cannot simply take like one model down and then bring in the other. TensorFlow serving is doing a pretty good job, and with the version manager and dynamic manager, they'll just serve it to the new one. But another model is basically, I can serve it to multiple models at the same time. And then whichever one answers first, I'm going to use. And this is the so-called rendezvous architecture. And let's maybe go through the implementation of that so we can understand how we do that, and then discuss why it's so valuable. So imagine we have an input Kafka stream. So, or Kafka, you can use any message queue. One advantage for Kafka is that you can actually have multiple listeners all subsuming the same message. So actually, like if our request is a simple Kafka message, it can be consumed by all those models in parallel. And then there's a second Kafka queue for the results. And then we have the so-called rendezvous component, which kind of picks the outcome and then returns that to the client. And this is actually helping us with multiple different things. So again, we can implement that solely with open source technologies. So this can be a Kafka queue. All of those I've seen can be simple containers, pulling from a Kafka queue. Here again, a Kafka queue, here another Docker container, for example. We can actually solve multiple problems with that kind of architecture. The first thing is, how do we update? So we have a new version of this model. We simply deploy that here, for example, model 3 into our architecture. And then in the rendezvous, we say, hey, only consider the output of model 3. And then we can step-by-step deprovision the outcomes, the containers running model 1 and model 2. This is one way. The other thing where I've seen that as being super useful is if I actually want to test a model against a live data. So one of the challenges of having like a totally new machine learning model in production, you retrain that, it might be a totally different architecture. You want to see how it behaves on a live data. And especially if you want to see, for example, also what is the characteristics on serving? How quickly does it react? How much resources does it take? So what does it cost me to actually run that? What impact is it going to have? And so with that kind of rendezvous architecture, what I can do is simply throw in like my random model in here, ignore the outcome, or ignore, basically not return it to the client, but record it in some kind of a database. And then after a while, I can actually compare how often did the outcome of that experimental models tree here coincide with those two models here, and then how long did it take, for example. So I can actually expose a model to a live data without necessarily impacting the response to the client by simply ignoring it / just dumping it into some kind of data store. The last advantage of this architecture is also I can actually make an ensemble decision. So so far we only talked about that here this rendezvous component is going to pick one of these three outcomes here, but it can actually make a majority decision. So it can just take whatever majority decision, whether this is a doc or not, was made by all three models, and then return that as a result to the customer. So this is kind of like one of the more advanced architectures. Of course, it's going to take more time and effort, resources to implement that. But overall, this is kind of like very, very helpful also later for exposing different models to live data streams. So the biggest advantage I've really seen with that and why we implemented that was to expose new models to live data without impacting results. So basically kind of like new model testing. So if I had to structure kind of the approach to how do we start with model serving, typically the simplest approach is either to take like one standalone TensorFlow serving container, which if we look at here, serving like a single TensorFlow model is kind of here in this path. So we export our model, we run our one container. So here, Docker run, we simply put it in here, and then we just can test that. So kind of like just build a simple API server around our model. The kind of second stage is then leveraging still TensorFlow serving or something. It gets more complex if you build it by hand with Flask by yourself. To basically leverage TensorFlow serving to dynamically update models. And we can do that by plugging in implementations for different sources. So as said, they also call that simply like a stream of different models coming in, and then turning them into a TensorFlow servable, then have our version policy choose whatever model we want to pick in the end. And as mentioned, it's called version policies. That can be different versions of the same model, but it can also simply be different classes of that same model for different constraints for different times. So for example, one other thing might be that you have different peak hours. So you have different user behavior during day and during night. So based on like the time of that request, so whatever client time is there in some request header, you might want to choose different models here in the policy. And then kind of like the search step, the most complex step probably is going to something like this rendezvous architecture, involves kind of more moving pieces, more resources, but in the end, it actually also enables other patterns which can be very helpful. The two tutorials or two labs we have around that are down here. So, so the first one is this one here. I think I just opened that before. And again, you can simply run that in Colab. And this is basically, hey, we save our Keras model. We can even see that. And then we just bring up our model server and just export this like one model here. So I think this is, as mentioned, this is kind of like the most simple approach to model serving. The more advanced stuff, and this is kind of then the second step where you actually configure TensorFlow serving overall. This is down here where you build it. And in the end, you can actually build your own gRPC server for that. But that's kind of like getting more complex, so I wouldn't recommend to get started with that. Just the longer you work with that, the more you'll see that you will end up with those challenges in updating models. And also, true, I actually missed that part, is you might want to try to push different percentages of data to different models. And this is, for example, again, also useful for model testing, or if you want to predict, if you have, imagine you want to predict click-through rate. So how often is a user going to click on a certain link? Usually that is if you want to play like show advertisement. You can actually do A/B testing. So in such kind of architecture, you can route traffic two different models. So in the rendezvous architecture, that basically means here in 30% of the cases, or 33, you're going to choose the output of model 1, 33%, you're going to choose the output of model 2, 33%, you're going to choose the output of model 3. And with that, you can do kind of like A/B testing for different models, and then compare the outcomes they actually have in the resulting click-through rate. The question is, does it assume the same input for each model? So yes, in this pipeline it does. If you actually, so especially here, it gets kind of hard if you have those if you have different steps in between. If you have that rendezvous architecture, as mentioned, typically those things end up being different Docker containers. You can also kind of combine the different pipeline steps, the different transform steps into that Docker container. So the question was, does this assume the same input for all models? As mentioned, typically it's useful if you have different classes of models with the same input, but especially with this rendezvous architecture, this also allows you some kind of decoupling and kind of merging this. So in theory, this can also be like multi-stage here in the middle. So you might have one container here doing the pre-processing, and then multiple containers here in the end delivering the scores. Okay. Okay. And that actually, as said, for me, this typically is this first important step I kind of would start with and focus on, because this again in the end is what's going to get you value out of your machine learning models. The next thing we'll look at is kind of like what kind of platforms are out there for this general model. And so if we had to classify that, so the two popular pipelines are probably TFX, because it's works really well with TensorFlow. It actually has grown a little out of just supporting TensorFlow. So by now there's also some PyTorch support from many components, and it's a very open community project. And probably what I like best about it, that it has inbuilt workflow orchestration with Airflow, or focused on Airflow. Then there's second thing is Kubeflow. So Kubeflow, it's actually, they have a lot of great tools. So for example, Selden for merging. Let's actually maybe open, do I have a slide on that? 1 second, yeah, here. So it's a pretty large ecosystem of different tools. So here we have PyTorch serving, TensorFlow serving, Selden core. So we already have like 3 different tools for serving. On the one hand, this is actually pretty nice. Of course, it gives us a lot of flexibility what we want to run. On the other hand, we still have to kind of make a lot of choices. And some tools work better together than others. Let's just put it this way. So this has really gotten better, quite much better with like Kubeflow 1.0. But still, there's a lot of work to be done to have like the same coherent experience across all of those tools. It's pretty Kubernetes centric, hence the name Kubeflow. And there are just a lot of different people contributing to it. The nice thing, which is kind of cool seeing, is that especially TFX and Kubeflow, they're collaborating quite a bit. So for example, the different pipeline steps, there's Kubeflow pipelines and Airflow. They're, for example, both supported here by Kubeflow. Then there are the typical cloud platforms. So I assume any major cloud vendor by now kind of has its own machine learning platform or even multiple of those. AWS, for example, has SageMaker, and SageMaker, what I really enjoyed early on, they had like a pretty easy serving solution, also supporting this A/B testing we talked about earlier, where I can say like I want to expose like a certain fraction of my request to model A and a certain percentage to model B, and then just compare the outcomes. And that's kind of nice. They support a number of open source frameworks, Spark, MXNet, TensorFlow. I think there's also, they're working on PyTorch, but they're, it's kind of like still very hacky, unofficial. Google Data Lab or ML engine. They also have TensorFlow, Keras, or TensorFlow now pretty much is also supporting Keras, so that's probably one. Scikit, XGBoost, and they have similar advantages. What you have to keep in mind, there was this question earlier about running in safe environments or enterprisey environments that you're exposing your data to those cloud vendors. Second challenge is that the more data you pipe through, the more expensive it gets. So often what I've seen is that people start out with those tools because they appear very cheap for the initial use case, where you have a little data, of course you have like your toy model being trained, but then over time, when you actually end up collecting large amounts of data sets, you have to shuffle around large data sets in and outside the cloud vendor. This is actually when it gets expensive. So it kind of, I mean, it's even less than linear, but it kind of feels like exponential growth as your data grows in cost. I said it's not really, but this is kind of like how it feels like. Most of those platforms, they have this workflow, and this is, again, this is kind of like the workflow we saw earlier. So this is SageMaker. I start out with my notebook. So this is kind of like my IDE. Then I can have jobs for like training, and I get like a large number of models which have been trained, or I can even import other models. And then I can simply expose them via an endpoint, which is then my model, and I can serve requests against that. I can A/B test or also shift kind of the different models behind that with something similar like as the version policy we saw in TensorFlow serving. Kind of the thing someone should keep in mind when building this open source. I mean, this is called open source, building open source pipelines, right? So there's a fair amount of complexity. So if we start out and just look at like the TensorFX tutorial, like we can just use Jupyter for data preparation, model engineering, and this is all there in the tutorials we have there. We can train our models, we can monitor it using TensorBoard, we can even debug it using TF-debug, and then we can serve our models. But what's kind of behind is actually like a lot of technology. So if we look at AWS, there's cloud storage involved, there's request streaming coming in, there's like data preparation using something like Spark. So there are actually like a large number of open source tools already built into this cloud pipeline. And if we do that ourselves, it's typically not just this like core pipeline of TFX, but we also have certain tools around for making this entire thing work. So for example, often we end up having something like Spark or batch stream processing, Spark, Flink, or a general Beam pipeline, which I personally am not a too big fan of yet, at least. Let's see how that develops. But basically something which helps me to batch prepare my data. I need some kind of data store, such as Hadoop HDFS, or being a database, being working for a database vendor, of course, yeah, database. And then often we also need to have like some kind of solution to kind of like stream our request and then serve some kind of endpoint with different models. So for example, having Kafka or some other message queue handling our request. I can also simply build that using, for example, load balancers or proxy servers on some kind of Kubernetes cluster. That could be the other option, but basically like some open source component of actually taking in our different requests and distributing that. Because I mean, here in the end, this might also be that this is failing for a certain time. We still need something providing the endpoint from where external requests can come in. So kind of that takeaway should be, even though it's already kind of complex to build this down here with something like TFX, there's still other parts we need kind of before that, especially for data preparation and data storage. Okay, then kind of to look at this part down here in more detail, TFX. So we've mentioned that already multiple times, and TFX, it's supposedly should mirror the production platform at Google, which to some degree it does, to others it doesn't. But what's kind of nice to see, this is pretty similar to the pipeline picture we had earlier, where we said, hey, this is actually what we want to achieve. So if we look at this pipeline, it's kind of like data ingestion, then we have data analytics, data transformation, data validation. We have our training, actually training our data set, evaluating the performance of a model, and then here logging, plus some serving, and then logging for performance. We have overall, what's also, I feel this is not really yet part, but can become much better. It's just like common data access control and kind of shared utilities across all this, all those different steps, and a common storage layer, which we'll also touch upon a bit more in detail later. So if we look at what's actually coming out with TensorFlow Extended, so what are the different components we can use? And again, this is all open source. So here we can pip install that. We can also just look at each of those components, each of the different codes. And so the typical flow of that is we have our example generator. So if we follow through the pipeline. The example generator, this is basically if we, for example, say for our training job, we want to split it into like 30-70 chunks and get like our validation data set out of here. And so this is kind of the initial integration endpoint. So I think here, I think I want to start with this picture. This is basically like the data ingestion part. Then TensorFlow is giving us a lot of different utilities to actually check to validate our data sets. And this is, again, this is kind of going back to what we said earlier, that actually data scientists, they spend a lot of time just dealing with a raw data set, before here in the middle, we can actually train our model. So we have the statistics generator, which is capturing general statistics about the data set. How does the distribution look like? And this is, for example, also super valuable if you want to track whether you have some kind of data shift. So data shift is basically if here in the end you're serving your model and some core characteristics of your data set have changed. And so if you capture the statistics of your training data set, you can make sure that this actually keeps same in your serving environment later on. Then you can generate a schema. And so this is basically how should your data set look like. And this also helps you to later on identify and validate your examples, whether this is still matching. Then next part is the transformation part, so the feature engineering part, and we touched upon that earlier, where we actually transform, where we normalize our data set, so we actually have a common input for our training job. So this can either be like an estimator or a Keras module, and this is where like the core TensorFlow comes in. So this is what we actually expect where we train a real machine learning model. Then once we have our trained model, we can evaluate it and validate it. And once it's being valued, so once we match our criteria, we can actually push it. And this push could then be either to some kind of shared file system from where TensorFlow serving can pick that up. So this is pretty much the workflow for TensorFlow extended. And this is kind of just the dependencies between the different components or what is consuming what. So it's just a slightly different view on that, where here's the example generator. It will basically just shows who's consuming from whom. All right, so this is the one system. And second one, as said earlier, is Kubeflow. So Kubeflow is kind of this a bit more open, a bit less biased, I would say, or a bit less opinionated, probably is a better term, as it has a lot of components in there. So here, TensorFlow Extended basically provides you with one workflow. You can use each of those components individually, but in the end, it's mostly sought to be used in like an orchestrated fashion using like Airflow or Kubeflow pipelines in this setup. Kubeflow Extended, it also lets you connect all those different components together, but it gives you some more degrees of freedom what you choose on the serving side, whether you want to use Argo or other tools, what machine learning framework you want to use, scikit-learn, TensorFlow MPI, and so on and so on. So that, on the other hand, as said, it makes it a bit more complex to configure. And sometimes one component doesn't work too well with the other. So, and this is actually the first lab where I would recommend that each of us is running through. So I will just skip over, and then I would give you some time to run through that. And feel free to ask questions. So this will actually go through the different components of TensorFlow or TFX. Did you restart the runtime? And so in my experience, this is kind of like really to understand what each of those components does. So for example, here the example gen split into training and evaluating data set, convert data into TF example format, and then just copy data over. Statistics generation, where we compute statistics over your data set. And this is also later useful, as said, for just making sure in your production system, if you capture similar statistics, that it still matches those to avoid data shift happening. schema generator. This generates that schema, and this is useful. I mean, you can skip over that if you don't have to, but in the end, your models will work really well if it's kind of structured input. So what we talked about earlier, this kind of like failure for this big automotive company who changed their transformation workflow, and then they didn't update the production environment. If they had like the schema validation thing, they could have actually caught that error. And the example validator also helps you to just detect anomalies. So often you might have just a corrupted, like a few corrupted lines in your data set, a few corrupted examples, and this will actually help you with those anomalies. Then the transform, and this is what we touched upon earlier, the transformation functions, which help us to transform our raw data into features. And once we have done that, yes, this is a bit more. Now we can start the actual training. And this is then running our actual machine learning job with an estimator. Okay, so, faster here. Here we also bring in, we can leverage TensorBoard to actually look at that, which I find useful to just see, for example, often when training, sometimes you have these really large runs where you actually have like a day of training or multiple hours. And if then early on you figure out, oh, it's actually not converging, it might be helpful to just keep like a tab open with looking at the output for TensorBoard for your model. Evaluators, then we have our model. Now we can evaluate it against the evaluation set. And again, this is why we here also have that dependency here with the validation. And then the pusher, basically, in this case, it's just going to push it to the file system, our local file system in the container, from where TensorFlow serving can then pick it up. So I think you can skip those down here. But this basically builds your overall pipeline. Before, and maybe we'll just do that before. Let's briefly talk about what Apache Airflow does for you. We also have some more slides, but basically, like, you have all those different components, and in TensorFlow Extended, there are actually Apache Beam jobs, each of them. So Apache Beam is kind of, let's look at the project. It's basically like a meta project, Apache. It's like a unified model. So imagine you have something which doesn't matter whether it gets executed as an Apache Flink or Apache Spark job, or Google also has internal infrastructure which kind of can run Apache Beam. So it's kind of the open source abstraction across a lot of different batch and streaming processing frameworks. And basically each of those boxes here is implemented as an Apache Beam job, but you still need some component kind of orchestrating that entire pipeline. And this is what Airflow is being used for. We'll touch upon Airflow later when we talk about the different orchestration things, but maybe just to get like a short impression of why we need it. Apache Airflow, as it was mentioned there. I was hoping for a nice picture here. But then never mind, let's find it here. Okay, I will touch upon the picture I'm looking for while you run through the tutorial. But it's basically Apache Airflow is a component orchestrating all those different things and making sure that the dependencies are being held. So you can first start transform after you both schema generation and example gen have run. So basically Apache Airflow allows you to build such kind of DAGs, directed acyclic graphs, which should kind of be scheduled then in a certain fashion. And Airflow allows you to kind of express those dependencies and then make sure this gets executed in the right order and also gets re-executed if something fails during that. So with that, I would actually propose that we've run through the TFX tutorial. So all you need is basically this link, and then we click up on, okay, let's go through that link again. So then we just click run in Google Colab, and feel free to ask questions at any time. I would now probably give like 10 to 15 minutes. Also, if you want to just grab a drink or ask more questions, now is a good time to do so. Also, as said, feel free to play around with the Colab environment a bit because it has those cool features. It doesn't really make too much sense here, but for example, you can just get also like a TPU or other runtimes, runtime support here. Okay, so there's already like one question. Based on your experience, how many engineers do you recommend to be in a team to deploy a production-ready TF pipeline? How does it compare to a Spark team? It kind of depends what you build with your Spark team, but usually it's comparable in size. So we're now just talking about the deployment, right? So you have your data scientist somewhere there building your models. And then depending on the infrastructure and how much you choose to implement yourself, if you just go with like something like TFX, I would say 3 people team probably is a good start. Then just the answer depends a bit. Is it just the team building it? Is it also the team operating it? So I would say like team of 3 to 5 engineers should be able to implement something like that. As said, like it depends like how many custom things you want, whether you want to build like a custom rendezvous architecture or not. Just if it then comes to kind of like operating that, you should just keep in mind like common teams setup. So for example, if you have on-call rotation for that, because that pipeline has to run 24/7, then you should have at least that number of engineers being up there and being able to be paged, considering someone getting sick, someone on vacation, and having different people between different weeks. So I would say like a team of 3 to 5 people for building. If you need to operate that, maybe a bit more. As said, I've also seen teams where this is actually a separate team. And then your data scientist building the actual models. If someone else has own experience to share, feel free to share in the Slack, or I think it can also unmute people if you also want to share. So this doesn't just have to be me talking here. This can actually also be input from other people. So maybe just the only thing to keep in mind if you ask about team size, I feel it's often kind of, if people have to estimate that in companies, it's too little, because the architects or people, this is the case for large companies, like the architects or managers deciding on the team size, they go through this tutorial. So especially here, like the TFX component tutorial, they go through that. Then they're like, oh, this is super easy, like one person should be sufficient. And this is the one thing I actually dislike about all those tutorials, because they make it super easy, but they hide kind of the real implementation pain of getting that up and running, getting monitoring up and running, making sure that scales. Yeah. The next question coming is, when would you recommend Kubeflow over TFX? So if you if you're in the TensorFlow ecosystem and you don't have too much experience, so you kind of want like a more opinionated setup, then I would actually recommend TFX. Otherwise, if you have a lot of experience and you're like, or you want to use some of those technologies which are not that well supported, you can actually, I would go to Kubeflow. In the end, it's kind of like converging anyhow. So you can also deploy TFX on terms on top of Kubernetes. It's a bit more work. So I would say kind of the different mindsets. If you have a lot of Kubernetes experience in your team, Kubeflow might be a bit easier. If you have like a lot of Spark, Bean, or big data Java stack experience, then TFX might be a bit easier to set up in your own environment. Overall, what I like about TFX is kind of this a bit more opinionated workflow, which works well together if you get started and you don't want to pick individual components together. Then it's slightly harder to deploy on Kubernetes. It's still possible. It's just takes a bit more knowledge compared to Kubeflow, which has been naturally written for that. And a lot of the components are actually the same. So, for example, if we look here, TensorFlow Extended also supports Kubeflow pipelines as like an alternative to Airflow. And Kubeflow is looking into similar solutions of supporting both. And also keep in mind, this is actually changing over time. So I think especially Kubeflow is moving pretty quickly right now and trying to get to like a more consistent experience. But yeah, as I said, it's changing over time. I would probably give like 4 more minutes for this tutorial, or you can also go back to some of the other links here and run them. And then continue with the automation part here. Okay, I think we can continue. Otherwise, if you need more time, feel free to say so. Overall, as mentioned, this is a lot of content, also with a lot of tutorials. So I think my goal is more to kind of like show you the different pieces and kind of give you an overview, and then hopefully you know where to continue from there. But as I said, if you want to deep dive into any topic, please let me know. So next part is basically automation, or I would call it the need for reproducibility. And so we'll look at like MLflow, Jenkins, Apache Airflow, Argo, and Kubeflow pipelines. And we have some labs around MLflow and Airflow. So the next biggest challenge, and this is again, especially if you're in constrained environments where you have to justify why a certain decision was made. So finance, healthcare, or wherever you actually make real big business decisions using the machine learning models. One of the challenges where currently is also a lot of research being done is around explainable AI. So basically explain like, hey, why did we make that decision? In one of the big things, also if you're looking for like certain compliance, like SOC 2 compliance or something like that, is that you can actually justify like, hey, this build was done exactly this way, and we can reproduce and retrain that same model from the same data set. So we'll later on go a little bit into the topic of keeping metadata. So basically being able to identify like, hey, this model here, which made that prediction, was trained with this version of the data set. But overall, it's going to often come up that you have the requirements that you need to be able to build a model exactly from scratch, maybe with like slight variations. Of course, there are like certain random components in there, but at best, you we even built solutions where we captured all the seeds to the randomized to the random generators. So you can do that to certain degrees, but overall you should be able to rebuild almost the same model from scratch. And so for that, you actually have to keep a lot of things in sync. And so most important, it's probably like the data set. Even if you append the data set, you should be able to identify like a certain version of that data set which was used for that. And you should also be able to get that back. So not just throw it away if you actually need it. You should make sure that you have all the same versions available. So if you trained a model with, if you trained a certain model, there are already multiple components. First of all, the code, so the specification you used for that, the framework version, so the exact PyTorch, the exact TensorFlow version you've used to train that model. At best, also the exact setup. So if you train like in a distributed environment, which we'll also just touch upon later, you should reproduce that environment to the best you can, because that's all going to have some impact on the model performance, or on the actual model being produced. And so there are certain tools to actually help you with that. And one with that in mind is MLflow. So MLflow is actually like a meta project developed by Databricks, so the company behind Spark, for example. And it has three main components. So one is tracking, projects, and models. And so tracking, it's similar to a TensorBoard, where you can actually record query experiments, and you can basically record metadata. Then there is projects, which helps you to get like a reproducible package format across any pipeline. In the end, it's a very simple description file, but if you recall that divide we had between data scientists and then the data ops people, and if the data scientists, if they're using different tools, XGBoost, MXNet, or TFX, then they don't want to tell the data ops people, hey, you have to run it this or this way. And this project, it just gives you a very simple abstraction to actually make sure that the data ops people, they don't really have to worry. They have to just run that project. And similarly with models, models, it's a general format for having like a common model format across different deploy tools. So again, this kind of helps you. It doesn't matter whether you trained your model with XGBoost, PyTorch, or something else. It kind of gives you this common tool. When using MLflow for that, you sometimes have to be a bit careful with the different abstractions. If that introduces too much overhead. If you're in like a very low latency environment, you actually want to expose a model with the fewest generalizations in between. But if in general you're in an environment where like not every microsecond counts, this really helps you to decouple the different steps in the pipeline. So MLflow tracking, kind of really straightforward, and like any kind of code you have, be it your machine learning code, be it your Jupyter notebook, you can just log certain parameters. So for example, here is number of dimensions, regularization factor, then during training, I can log accuracy, and then I can actually, I have like this nice UI, I can search for different runs. So for example, if I later have like a large number of models being trained and I want to find all the ones with accuracy above 0 dot something, I can just find all those models or all those different runs, and then also get an output of those different models. I can also log other artifacts like real models, like a pickle file here for my actual models, or certain artifacts where I produce some images. So this is kind of like a tool to kind of keep track of such kind of parameters. MLflow project, as mentioned, this is a very easy way of encoding your entire environment into a project structure, which you just simply can give someone. So here, MLflow run example project. This can be executed by anyone, and it can put like, in the end, I'm most likely going to put like something in here like Python, or I can also build a container with the exact XGBoost version I used to run that. But it basically allows me to bring in all my different parameters. What I actually forgot to mention, if you want to make something reproducible, is you should actually capture your entire environment. So not just the version of that training framework you use, so the exact PyTorch version, the exact TensorFlow version, but basically any dependency also should be versioned. And this is also here, this is the Coda environment of MLflow. They also have kind of the container variant. This allows you to capture the exact Conda environment you use to execute that. So it's actually not that much. It's a simple YAML file, but in the end, this makes it super easy if you're getting started somewhere to get like a reproducible run and to force you to kind of capture all your dependencies in an environment. So if we want to look, for example, at one example, link here. So if we just want to see how that looks like. So here, in the end, basically my project, can be a container, it can be just a GitHub project, but it's a very simple format. People can look at, people can version. So this is something I can store in Git. This is something I can version and run over time. And basically just here I record all my dependencies with hopefully the exact version number. So I make sure this is what I want. I get a reproducible environment. And so this is kind of the core idea of MLflow, to give you an easy structure for sharing and having a reproducible build of your project. MLflow model, it's very similar. It kind of gives you a way to train your model, and then also just make it easy for people to run that no matter what kind of thing you trained it with. So here I have different flavors, and they support basically like any format. So anything I trained it with is super easy to run in this kind of abstracted model format. Of course, there's going to be some overhead. Again, let's go here once more. Still open. So if I really care about a very low latency serving, I probably wouldn't use that. But if I just have like a general architecture, the data ops people, they don't have to care whatever that model is. They can simply run it using MLflow run. So that sometimes makes this serving problem a little bit easier. I wouldn't use it for low latency production deployments, but especially for something like just like a test ecosystem, it can be super useful. So in my experience, the part I used most from MLflow is just kind of the project packaging part, because it gives you a way to actually structure and version your projects, which is super nice. Imagine that evolving over time. We saw the GitHub repo before. So actually like a project can just be versioned in Git with the necessary dependencies. Which in my opinion is the biggest advantage of MLflow. So here we can use MLflow for serving, but I think that's okay. Are there any questions to MLflow? So I would say kind of the core takeaway is, and this is actually what happened to a number of projects where we started out with that. This was super useful as a format to start out with. But over time, we identified like some other kind of formats, so we kind of evolved on that. But as this is super flexible, it suffices for a large number of project setups, and it really helps you to get started and capturing an MLflow and machine learning project as an entity. Okay. Orchestration. So question is, how do we actually execute and schedule all of that? We talked a little bit about that earlier when we looked at TensorFlow, Extended. But overall, I think we care about what other open source options are there. And so what choices do we have? So when I started out building that, Airflow was out there, but it wasn't really production ready in my experience. So actually what we did for the first pipelines we built, we used Jenkins. So Jenkins is like a normal CI/CD tool. We actually built a CI/CD pipeline for this part. So the data scientists, they would build their models, and then once they had kind of built their first model function, they would submit a CI/CD job that would train a model, that would test a model, and then also push it to model storage, and then continuous deployment if it was actually up to certain performance characteristics. This would push it over into the serving environment. And probably that still works for many use cases. And this is also what Argo, what happened there? Argo, one second. This is, for example, what Argo also is about. That is the thing I'm looking for. Yeah. So it's basically like a native workflow CI/CD system. So it's kind of like advanced Jenkins, advanced workflow on top of Kubernetes. And this is what I also see more and more being used for scheduling such kind of machine learning jobs, especially if you're in a Kubernetes environment. The other tool I find super useful is Airflow here, because we can build this general DAX. So DAX is a directed acyclic graph, and this can basically have those different dependencies here. So for example, this again is the TFX example. So we have our example generator, like the CSV example generator. We generate our statistics, then we generate the schema, and then we have our example validator. And we can build like general graphs like that, and then Airflow is going to make sure that this gets scheduled in the right order. So also, for example, if this fails, it knows what to re-execute, where to keep results safe, and it also really helps you to estimate like how long is it going to take. There's actually a pretty good tutorial on that. And for me, this is a mixed tutorial of learning about TFX and learning about airflow. But I would recommend for anyone who is interested in job orchestration. So how do you schedule jobs across such kind of distributed infrastructure which depend upon each other, to look into this. I wouldn't run that now because it's actually fairly complex. I think there was a nice graph somewhere in here, which here. So this is the part I wanted to show you. So basically you can just step by step in that graph, you add like one job after the other. So we add our example gen, and those are the dependencies. And then we just add them step by step here into that job. And this is actually this workflow is something we can also version. So as we, with MLflow projects, we talked about how can we version a certain project. This is actually another way I can create an artifact capturing that entire pipeline. So this is, again, something you should keep in mind, like, how do I version an entire pipeline? How can it evolve over time? And what's kind of the project artifact structure I want to capture here? And so, for example, I can also, I can actually put that also into MLflow as kind of a dependency and an Airflow job. Okay, and then we add more stuff. So we add the transformations. So here we kind of can build like our pipeline step by step. And this is why I actually also like it, because it really helps to once more understand the different dependencies of the components in TFX. So I would say this is a really highly recommended tutorial. And I wouldn't tell you to run it right now, because it's taking quite some time, because it's not as easy in a collab environment. So it takes some more work, but it really helps to understand Airflow and other things. Kubeflow pipelines is still kind of the alternative, but first of all, it's still in beta status. And I see more and more projects kind of favoring Airflow over Kubeflow pipelines. And I personally also prefer it, but I also heard of other people who prefer Kubeflow pipelines. So there's probably this and this side. In the end, it's actually pretty similar. So you can kind of create your DAG of a pipeline, and then this generates some code. And this, again, this is the thing you want to version later on, because it versions a certain step of your pipeline, or a certain architecture of your pipeline. And then I can basically run that pipeline. I think the rest is, it's interesting to look into what actually all happens here, but it goes above the contents of this workshop. Argo, as mentioned earlier, is similar. I would say it's not so much focused on workflow orchestration or scheduling, even though it can do that. It kind of adds more the CI/CD style you might be used from Jenkins. So it's not like this drag and drop, it's more like I specify my CI/CD pipeline, but in the end you can actually achieve similar results. It kind of depends on the field, or also what you're used to. So if you come from like a CI/CD background, Argo might be the easier thing to use. If you only run on Kubernetes, Kubeflow pipelines might be a cool thing to use. If you want to run across different style of environments, so Airflow, again, is one of those projects which has its inheritance in this Hadoop Spark related space, then you might be happy with Airflow. As said, for me, Airflow is a pretty scalable, pretty cool solution, but I would recommend to actually investigate what's best for your use case. Apache Beam, we also looked at that before. So Apache Beam is kind of this general way of representing either a Spark job, or abstract a Spark job, a Flink job, and then this can run on any architecture, on any executor. And so in terms of TFX, each of those boxes is actually an Apache Beam job. Okay. Model management. So so we now trained our model. So we have this pipeline, we can reproducibly train our model. How do we continue from here? Or also kind of like, what is the more advanced thing of retraining and retraining different models? So we look a little bit at TensorFlow Hub and Dask, especially the Dask hyperparameter optimization. This is actually just as a reminder, what we touched upon before. So if we have trained and pre-processed our model, so we created those features, we cleaned our data set. This is something super valuable and something we should make sure we can actually reuse between different models. Because yeah, we said multiple times, this is where data scientists spend like 70% of the time. And this is something where a concept called feature catalog or feature store, different people call it by different names, comes in super handy. Maybe just one example. Imagine we're Airbnb and the first data scientist is creating a model predicting some kind of user behavior. So what kind of feature does he need to generate? He needs to generate some kind of representation of a user. So he's gonna create a user feature. The next person comes in and needs to create another prediction about users. And for him, he doesn't have to start from scratch, like writing the same cleaning routines, doing the same work the first guy did. So he can just look at that feature catalog like, hey, which representations, which features representing a user do we have? And this might be, first of all, multiple, and it might not even be totally fitting for his job, but he can at least reuse, discover and reuse what other people have done. And again, this can be on like 2 levels. This can be reusing just the code they've written to clean and pre-process a data set, or it can even mean if that's something large, like Airbnb has a lot of users, so running that pre-processed job across the entire user base is something prohibitively expensive. It can also just be like a cache where I create that and then I can actually reuse the already pre-processed data set. And I've seen people who actually built that with like a daily job, always creating the same features over and over again. So Airbnb actually have created something called, I think it's called Feast. Oh yeah, Feast was someone else, but they basically created this feature store where they can share those pre-processed data sets. And this is something which, if you have reached a certain size of your company, which is going to really help you to get more value out of your data science team, because not everyone has to pre-process all the same data from scratch. So what happens is kind of like, hey, you have your raw unstructured data, feature engineering, it gets stored in that feature store or feature catalog, and then the model training is picking up those different features from here. Again, this abstraction can help you to introduce something like caching or different versions. So if that version of the user representation is evolving over time, it can also help you here. I would say that's nothing I would start with as a first step if you're building a pipeline. But if your team grows and you see that, especially the data science part of your team is spending a lot of time on creating those features, I would say it's worth looking into that. Or the other part, if creating those features is computationally really expensive. Of course, you need a lot of compute resources for that. You have really large amounts of data. Then it might also be worse to introduce that actually as a cache in the middle. Next thing to look at is, as mentioned, this training loop, we don't do that once. We do that many, many times. This often comes by with different hyperparameters. So for example, it's really hard to estimate how many layers we should have in our neural network. So often this is actually a hyperparameter, and we'll test, hey, is our network better with 1 layer, 2 layers, 3 layers, and so on and so on. The other very common parameter is the learning rate. So how quickly do we want to update parameters across a network? And that can actually also give you very different results across your run. If you update too quickly, you might miss the best model. If you update too slow, training is just going to take forever. So this is also something, one of those hyperparameters you really want, you typically want to optimize for. How can we search that? Typically, those hyperparameters, they are like a high dimensional space. The easiest way is basically just to go like through like, first test this, and then this, and then this, and so on. And often we can also, the data scientists will know by experience what are kind of like the crucial things. Is it more the network shape? Is it more the learning rate for this kind of problem? And there, for example, I really like Dask because they make it easy to play with that. So for example, they have like here, this is grid search, where you basically just search the entire grid. We can also have like something like random search or more guided search towards finding the best set of hyperparameters to work for us. The thing to keep in mind is that each of those loops is going to add considerable amount of resources, because basically we're training, spending like a lot of time training that model. And this is, for example, where it's helpful to also have like early stopping parameters. If you see that a certain combination of hyperparameters doesn't work at all, you either, if you want to do it manually, you can look at like a TensorBoard and see, this doesn't perform, so just abort, go to the next set of hyperparameters. Or you can also just have like an automated solution with like a threshold, which says like, after 20 iterations, we are not really converging in our training, so let's abort this run. Dask, it's something which I would say it's worth trying out and playing with, but I would say it's kind of like an optional thing. So it's for some companies, it's a popular machine learning library. It gives you like a lot of stuff and it nicely scales. But I would say it's not really required for this workshop today. The next thing to think about is actually model optimization. So we kind of retrained our model and now we think we're done. But actually before serving, we can do a lot of different optimizations. And the first things, or the kind of trivial to think about things to consider are different serving environments. So do you want to serve it on a mobile phone like this one? Do you have like a GPU environment? Do you have a CPU environment? Do you have a TPU? Do you run it in a car? So there are kind of different serving environments to take in mind. Also, it's kind of like serving performance, or how small can your model be? So often if you train those first model, it's like you can end up with like several megabytes of models. And then there are several optimization techniques to kind of trim down that size and also improve execution time without losing too much performance. The one thing, if you want to have something for mobiles, is, for example, TensorFlow Lite or TF Lite, which helps you to, first of all, strip down. So there's a TF Lite converter, and then basically make it easy to integrate into iOS or Android apps, and so make it executable on phones. And keep in mind, like this model, that might actually be the same thing you run here in TensorFlow serving on like a large cloud server, but then you additionally used the Lite converter to make it into a smaller, maybe not as a precise model, but much smaller and much faster to run. So overall, what we want to achieve is either, usually it's often they actually come together. So either we want to reduce latency, so we have this huge model which actually takes like half a second to make a prediction, because it's like a multi-layered network and it has to run through that. Or just cost, that it's simply too expensive to run because it requires too much memory. So typically memory is the constraint I most often have seen. And so we want to reduce that. Is edge devices, so that can be a mobile phone, that can be a car, or like a remote thing where I actually don't have that much power where I want to run that. And also if I just saw that once, but I found it interesting, where just updating the model was like with some remote factory or construction site, where they actually was super expensive when we ended up with like a 500 megabyte model to just transfer it there, because they were retraining it twice a day. So they actually just wanted a smaller model so they could just update it more quickly. Another interesting thing to consider is, like, if you run it on different hardware, what is the fixed point performance? So for those of you who might not be familiar with that, we're dealing with a lot of multiplications in such kind of network. So it really matters, like, how precise can we represent a number. And there a large set of research has gone into optimizing that. So it's basically on certain hardware you cannot, or it's really expensive to represent floating point operations to double degree. So it might be much cheaper just running it in with like single performance. Single precision was the word I was looking for. And there are multiple techniques for that. So we can reduce the overall parameter count with structured pruning. So basically either dropping layers, or if we have in a neural network some kind of edge which is just like almost zero, we might also just prune that away. We can reduce the representational precision with quantization, or even update the original model topology with reduced parameters for it's like very advanced techniques. Here's the first two especially. There are standard tool sets for that available. So for example, there's, first of all, down here is a link for optimization guide. So similar things exist, for example, for PyTorch or XGBoost, but this TensorFlow model optimization kit, it's a pretty cool thing to try out. So we're mostly going to talk about this here. So let's go forward. So I can do actually quite a bit. So here are kind of the different transforms. I can strip unused nodes. So which nodes in my neural network are not used at all, just strips them out, reduces the number of multiplications which have to be made, folding constants, and especially like quantization is a pretty powerful thing. So why does that work? So if we think about the different precisions, so when training a neural network, we want a very high precision, simply because of when training a neural network, we're doing forward propagation, backward propagation, forward propagation, and so on and so on. So basically, errors accumulate rather quickly during this procedure. So when training a neural network, we often tend to want to have like a very good representation and very precise representation of the numbers we're dealing with. But when serving, we're actually just doing one pass through the network because we just have to do one prediction. So actually errors are not going to accumulate that much. And the second advantage is we actually know the range. So when training a network, numbers might be like very low, very high. But when just doing serving on a final network, we actually know the range of numbers we're dealing with. So with that, we can actually pick like a lower representation, also taking up less memory. So from going from floating point 32 to floating point 16, we reduce the dynamic range, so the precision we can have, and also the min-max values. But at the end, this is going to result in less memory. Google even came up, also other researchers came up with own data types and own floating point representation for neural networks. But this is something you can easily use on a trained model to reduce the memory footprint. And often this also reduces the latency simply because, for example, GPUs, they are still faster on single floating point performance compared to like double floating point performance up here. So all those optimizations, and here they've even listed more. So quantization, dynamic range, this can really help you to reduce latency and model size. Good. Next thing is kind of how to run all of that at scale. So basically how to distribute TensorFlow. Most of the examples we've done so far are running on like a single CPU and a single node. If we have really large problems, we might need a large cluster to run TensorFlow, PyTorch, or any framework of choice. And there we actually have to consider how to distribute that. And this is a bit harder than one might imagine at first. So the challenge is that in the core architecture, TensorFlow is kind of having workers and parameter servers. And then there's the scorer, which we can leave out for now. So the workers, they're actually doing the matrix multiplication, so the actual mathematical work. With the parameter servers, they're therefore distributing the updates. So basically, he's computing one value for a certain parameter, but this guy actually needs to know it as well. So they're kind of like the communication hubs, the distribution hubs. And so we kind of have, with that, we already have multiple options depending on the size we need for our network. So if we have multiple servers, we might just have a single parameter server, which just takes all the different parameters and then averages them. So worker A says this should be 0.5, worker B says 0.6, 0.4, so we're going to just average that to 0.5. If that's too large, so if we simply have too many parameters to be handled one by one single node, we can also just average that across multiple servers. So this is kind of the first thing, how we can scale things out. The second challenge is basically those updates. So they all have to be sent here. So those communication lanes, they quickly become a bottleneck. So there was the Horrorwood project by Uber originally, and they proposed an algorithm which first came out of the MPI, so kind of like parallel computing world. and they have kind of this optimal way in which they exchange parameters. So this is kind of like bandwidth optimal. So it's kind of proven that this is the fastest way in which they can actually exchange the updates. And here it actually happens without the parameter service, so the workers are directly exchanging them. This is actually implemented in TensorFlow 2.0 in the different distribution strategies. So this is here. If we look at that, we could even run that as well, right? We have those kind of different strategies in which we want to distribute things. So by default, we simply mirrored that, but we can also switch back to kind of like to other things like one device and so on. So keep in mind these strategies, they really depend upon what you do. So how often do you update your parameters? How quickly should that converge? And convergence is actually another interesting point where you have kind of the, in many frameworks, you can choose that. It's basically, do you want to do that synchronously or asynchronously? So imagine where all those are computing. So worker A in like one round, so kind of like one batch of updates, they all updated this parameter. Can worker A continue before worker C has stopped, or does he need to get the updated parameter first before you continue with the next round? So if you kind of have this asynchronous approach, it adds a bit more random because it depends upon which updates are being seen by what worker. But overall, it's going to be faster because worker A doesn't have to wait for any stragglers, which might be slower for certain reasons. So yeah, this actually, so this comes down to the different choices you have when distributing TensorFlow or distributing like any machine learning framework. So first thing, and this is what we just talked about, synchronous versus asynchronous. Between the different batches, do you want each of them to be synchronized to have more predictable upgrade and also more reproducible upgrade? Or are you okay with asynchronous updates, which usually is going to result in faster speeds? Then it's the question whether you want to have the all reduce, whether it's the parameter service. So all reduce, it means that the workers are actually exchanging the parameters between them, whereas parameter service, you have dedicated nodes, which usually also have then higher memory and maybe even like a different network connection for just handling the parameter updates. Next thing is whether that's a pretty simple choice, depending on the size, whether you actually need to scale your one framework across multiple servers. But if your one framework is actually small enough that you can like run one iteration on one server, so you can actually save this entire overhead and parallelize by just having different runs. So as mentioned, there is a different hyperparameter runs. If that's actually sufficient that a single run fits on a single machine, distributing becomes a whole lot easier because you're reducing all that data transfer. Next choice is then CPU versus GPU, so like on node thing. If you're running in Google environment, or they also now have kind of like small things you can attach somewhere else. So basically like replace TPU with like any accelerator hardware being out there nowadays, which typically is attached externally to a node. So at least you have like some bandwidth limit to this external device. So this is the other thing. Yeah, whether you want to do it eagerly, so distribute up front, or compute the entire graph. This, I think I had some hidden slide on that, but this eager, that's, just look at, I think Yeah, here it's basically, this is also possible in TensorFlow itself. And it kind of depends upon how you want to construct your graph. So the original TensorFlow approach, and you can see that, was like you create your entire graph first, and then you say like run. So here you see like, hey, now we do that like 1,000 times and we train it. Whereas PyTorch, or the eager execution model in TensorFlow, is building that graph on the fly. So you see here, here's like our range loop, and now we build this on the fly. And there are basically trade-offs between those two approaches. So the eager approach is super useful if you're doing exploratory analysis. So I can just write like a print statement in here and have like some debug output in the middle. I can also have like early stopping conditions. If I see something, if the loss is here too high, I can just skip the rest, which is like much harder here, because here I built the entire like graph at first, and then I run that. On the other hand, if I kind of use the graph approach first, of course, then TensorFlow can optimize much better because it has the entire graph and it can optimize for that entire graph. So those are kind of like the trade-offs of what API to use, whether I want to build my graph eagerly, which in my experience is good if you're doing kind of the first steps and you explore your data sets. Whereas for production code, where I have my final model, I just want to run that as quickly as possible. Building the entire graph first, in my experience, allows the machine learning framework to have more optimizations. Okay, distributed training with TensorFlow. So here, there's another Colab notebook, and I would leave it again up to you to run that on your own. Here it might really make a difference. What runtime we use. Connecting, initializing, change runtime time. So whether I pick a hardware accelerator or not. So for example, if you choose the TPU settings here, you actually first need to enable the runtime time to TPU, which requires restarting this. I would recommend this tutorial to you if you're interested in running distributed TensorFlow, or just to understand the different models, because I think it really helps to run it once. Also on the slides, this is why I didn't want to go into like too much detail. It quickly gets confusing for me at least, if I don't see it together with code. I'm really like that person who likes seeing that with code. But as I said, feel free to also ask questions. Otherwise, I would actually recommend to run that notebook, this notebook here, with different settings and different strategies. Okay, so this is the distributed TensorFlow, and for many other frameworks, this choice of eager versus graph, this is something which I would say actually TensorFlow took over from PyTorch. So PyTorch also always had this eager mode, which I guess makes it more suitable for researchers. But typically you have similar options for other frameworks as well. The next challenge, I would say, comes up to kind of libraries and sharing code. So first of all, building and training those models, similar as like creating those features when we talked about feature stores, is something which is expensive. First of all, in terms of investment into people power. Secondly, into investment also into compute resources. And so for that, it actually makes sense to share models. So there's TF Hub, which is a public platform of sharing code. Here we go. So here there are a lot of pre-trained models being available. So it often makes sense to, for example, pick up a model for images, and then I can do something called transfer learning and actually retrain that for my particular purpose. So transfer learning comes in, for example, handy. I don't know, I want to develop something recognizing street signs in Sweden. If I already have a model which can do general street sign recognition, I can take that, and then I just need a much smaller data set to kind of like fine tune that to the Swedish street signs, as opposed to the more general set. So often starting with like a pre-trained model, it really allows you to reduce the amount of data you need to fine tune it, and also the amount of compute resources you need to invest there. So, the other thing, I think this is the backup slides here. There's this one task for like, if you want to run it on Spark together with TensorFlow. This is one really good talk. And the other thing we talked about already earlier, I just moved that back here, is basically like for testing, coming back to like, how can we actually test our models, because that's something you should keep in mind how you do it, because like writing something like unit test is very hard for models, because we're actually doing probabilistic things. We're not having this one output and then it's incorrect. So in my experience, what works really well is, first of all, having like a good set of testing and validation data sets, like holdout data sets you haven't used to train your model. But then in the end, it really pays off to expose it to live data and just compare kind of the outputs to that. So A/B testing with live data, either directly using the output, or at least kind of record it so you can differentiate like, hey, model 2, which we have used for the past half year, always made that prediction. And on those and those samples, model 3 disagreed. And then the data scientist can kind of look into that and say whether that's better or not. Okay, monitoring. So having something like TensorBoard is super useful. I said, like also for just earlier boards doing training. And there are similar tools for other machine learning frameworks available as well. The tool which has really saved a lot of time over the past for me is kind of like TF-debug. And initially TF-debug was just this command line tool, which was a bit clumsy to use. But since I integrated that, I think like since 1 year ago in full production, or 1.5 years ago, it was already there. Since I integrated TF-debug into TensorBoard, it really makes it much easier to look into and understand what's happening in your model during predictions or during training. Okay. The other thing you should get used to, and I mean, again, just coming back to what we discussed earlier, that we should establish similar practices as we already do for normal software engineering. And in normal software engineering, what do we do if we have something performance critical? We profile it. Similar with machine learning frameworks, if we want to figure out, especially when using like expensive devices like TPUs, where do we spend most of the cost? It's profiling really helps. So there with profiling, it's still kind of like, it's an art where you need to understand certain memory access patterns. So often especially GPUs, they have certain alignments. So if you use multiple of like 16 or something, your model will run much, much faster. And this is something which typically grows with experience. So if you just try out different values, and while profiling them, you'll see like a big performance jump. So often those are like really steps. So that's often really useful for profiling and just building up that knowledge, especially about expensive devices. So either external accelerators or even internal ones like GPUs. Last thing is like resource and service management. As we already talked about, like a lot of components here, having a platform where you can deploy that, such as probably like Kubernetes, cloud environment, or if you already have like Apache Mesos, or D2IQ, DCOS, really makes sense because you will need a lot of hardware resources, and typically you want to share that between different people. So this is also why, for example, like Kubeflow or also TFX, they often are often deployed on top of Kubernetes, simply because that allows you to kind of decouple the actual nodes down here from what's running on top. Okay. The kind of last topic I would like to go in is the metadata topic we touched upon earlier as well. So when working in healthcare, so let me start with that, we had that challenge that we needed to be able to identify, here in the end, we had like our model, here at the beginning, we had like a data set, and as we were dealing with patient data, it was crucial for us to figure out like, hey, this model actually depends on this patient record. So if that patient says like now all of a sudden, hey, no, you cannot use my data anymore, we at least wanted to be able to identify which models are being impacted by that. It's still a pretty ongoing discussion whether how under GDPR or CCPA that's impacting a model being trained with like sensitive data. But in the end, there's actually like, this is a paper about it, is like how much data might eventually be exposed in the final model. And so this paper actually says there's a memorization effect, and that might actually expose like a lot of sensitive data in the end. So it's something we should at least be aware of. And so when we actually needed to figure out like how does a data item here reference to a model here, this turned out to be pretty cumbersome because we had to go through, identify a data set. Okay, that was easy because we just knew like, hey, this patient data was in like this data set. Then we actually had to figure out like, hey, which features were being built, or how was this data set being transformed into which features? So that was kind of like data store number one. We had to look at our data connection number one. Then which models were being trained by this data set? Which ones did actually make it into model management? Which ones were being thrown away because they didn't have good enough performance? And then which models were actually, which of those models were being served here? And if you even want to have like an additional step here, this can also be like, hey, this prediction was being made by this model. So if we're talking, for example, about finance, about credit card ratings or credit card approvals, there might even be like one more step here. Similar, like inside here, a feature might actually be built from another feature. So there can even be like a self-link here. So this can turn out to be pretty challenging to understand the provenance of an entire model, and even to understand the entire version history, especially if you have multiple versions of a certain data set, so that data set keeps on growing over time. So you actually need to be able to understand like, hey, this is from this point in time, and this is also from this feature version at that time. This is also crucial for audits, at least it was for us, but in actually any audit, in any auditable machine learning environment I've worked, this was kind of important, where that you could actually like say, hey, this was coming here from this data set. So for example, this also impacted a little bit which kind of audit logging we had to do in the backend here. Similarly, like if you onboard new people, you might want to identify reusable steps. So kind of the idea of like the feature catalog, do I have to develop a new user model, or is there something I can start out with? Also proved out to be a challenge. Similar like, hey, is there actually already a model I maybe just need to fine tune? Comparing about different models. So if I have different models like the AB model we talked about in production, I want to compare the performances. How can I relate that data back? And then also is actually the data distribution, so the statistics for my training data similar to the statistics coming in here for my serving data. So this is actually where we started to build out a common metadata store across that entire pipeline. Of course, initially, like most of those tools that have like their own kind of metadata tracking, like, hey, this feature store, this data store, but in the end, then you have to manually merge that across all of them. So this will be pretty cumbersome, and it took us like a day for this one example to figure that out. What do we mean by metadata? If we say like a common metadata store. So Kubeflow actually has some kind of definition which I can live with. Metadata means information about runs, models, datasets, or other artifacts. So artifacts is basically anything being produced here in between, like a dataset here, a feature here, a model here, serving statistics here, and so on. So if we look at what that might mean, so it might mean information about a data set. It's not the data set itself, it's a data set version, name, creation history, and I would always recommend to have like some kind of SHA value, some kind of hash value, so you can actually identify this hasn't changed over time. Then my transformation outputs, those are other artifacts, the features, notebooks. So I can basically retrace exactly what has happened throughout this entire pipeline, throughout this entire ML project. Similarly, like train or test performance, this can also be metadata. And yeah, so this basically kind of allows me to track everything which you might have created, which might have been gone into creating this entire model. And this is kind of where I come back to another open source project we actually created at ArangoDB. It's called ArangoML Pipeline. So it's an extensible metadata layer for machine learning pipelines. As mentioned, ArangoDB is kind of this multi-model database. And so we created a layer, API layer on top, which easily allows you to capture that metadata for machine learning pipelines. And the reason why we did that, and we actually did that before I joined ArangoDB, we started that at my old company, is that this multi-model aspect comes in very handy here. So again, let's recall what multi-model means. It means we can store kind of like documents, like a MongoDB code, but we can also store and query graph structure rather easily. And in our use case, this turned out to be super valuable because like each of those representations, like the data set representation, I can store in a document. I don't want to really hard code, have a fixed schema for that, which I would have to have if I use a relational database. But data sets from different sources can have different metadata, similar with different transformations, different features, different statistics from model trainings. It really depends on the framework I use. Then also the model stats and so on and so on. So that's where actually like a document store can shine because I'm not bound to a particular schema. But then on the other hand, we wanted to capture the relationship between those different entities. And this is where graph store comes in really handy. First of all, for representation purposes, but secondly also for query purposes, because now this query like, hey, this model, or from this data set, like which models are being impacted, it's simple like a graph traversal, like in this graph, which models are being reachable from this one data set. So it actually makes it super easy to represent all those queries. So in the end, kind of like this metadata, it's super useful for a lot of different entities in your team. So first of all, the data scientist, he can find relevant entities for a given model. So he wants to debug like this one model having bad performance in production. He can easily figure out, hey, this is the Jupyter notebook. This is the model, this is the data set. He can explore performance differences if this is logged. He can check like during that training run for that model, what were the test and training performances. And he can also just search existing entities to create something new. The data ops person, and this is kind of like where we originally intended it for, he's safe for audited, he can do trace data lineages for GDPR. He can provide reproducible model building because he actually knows like what artifacts have gone into here. And it also helps to detect this data shift where all of a sudden the requests coming in into my production setup are way different from what we've seen earlier. The traditional kind of like administrator or infrastructure owner, even for them, it turned out to be super helpful because they can actually do resource accounting. So how many resources were spent on like this one project overall? So how many GPU hours we spent on training this one model across all runs, also the ones we threw away. And also for permission tracking, who is actually allowed to access what. Let's skip over that. It's a simple Python package, comes with a UI. And so I think this is kind of the tool set. There are other people now also coming out with that. So TFX is trying to add also a metadata store. Did I have a slide on that? Yeah, the TFX integration coming up. And also Kubeflow is also looking into that. So kind of the takeaway should be like, this metadata is actually something very valuable. Here's the slide I'm looking for, because it allows you to actually operationalize in those enterprise environments, especially. So if you're in constrained environments, keeping track and keeping audit trails is probably a requirement your security team is going to ask you for. And therefore, keeping these provenance or related metadata across the pipeline is an important step. You can also solve by a number of open source tools. All right, so I think here people are writing that there are actually other workshops starting. And I would also propose that now at 8, it's probably a good point to cut from the presentation part. I will actually stay on this call. So I would recommend now, we saw a lot of different tutorials. So now would be actually a good time for you to run through them. I'll just be here to answer, first of all, questions you might have for those tutorials or help you if you need any help. Otherwise, also feel free to ask now any questions still on the Slack, on the chat here. And there's, for example, one, in your experience, where does the front end Kubeflow Airflow lie in the structure? Okay, let's go back to the structure. So I think it kind of like, where does this here lie in this kind of structure, right? So the Kubeflow Airflow, this is typically relevant for in 2 parts. So first of all, it can be relevant in like the model engineering part where it builds as an initial model. And I then hand that over as like one project to be run to my data ops team. So it's relevant for the data scientist to build that. And there it's often in simply like a container. then in the second part is here for the data ops team, which probably wants to have like a consolidated view across like all the training going on. So those are the two kind of views. And there's a clarification in your TensorFlow training, for instance. Where is he? Oh, so I think that front end, if I understand your question, if you run that tutorial for Airflow, it's simply going to run that UI inside the container. So the tutorial should just give you a link to expose that. So in the tutorial, it's just going to run on the same instance, on the same container. And this is, as mentioned, this is similar from like the data scientist perspective. Often for them, it's easy enough to run that in their own instance. And that's also just like a single node Airflow. If we have this large second part here, that second part of the cluster here, then we actually have are typically dealing with a distributed infrastructure. I'm just looking for one slide to dive into here. So basically in this part, often the UI is just going to run in that same container where I'm running it. Here, I would have a distributed Jenkins, a distributed Argo, or a distributed Airflow cluster. And there the UI typically will live on its own instance. Because then the data ops person here, he can just is going to use that one UI here. Any other questions? Okay. Otherwise, then thanks for holding on for like 3 hours by now. I hope there was something helpful. Feel free to ping me with feedback. I typically, what I do, I keep on improving the slides over time. So there might be additions. So if you ask nicely, I'm more than happy to add more things. And then I said, I would actually recommend now to pick your favorite tutorial. You probably won't have time to run all of them in the next hour. But just run those parts you're interested in, and I'll stick around for another hour for questions or helping you with the interactive part of the tutorial. Thanks a lot. And yes, I'll still be on, I'll just mute myself, but feel free to ping with questions. I can also unmute again.